Hi, I'm Bernard Kufluck, and I'm the Watson IoT Platform Product Manager. I'm going to take you through a demonstration of the Watson IoT Platform, and we're going to go through a scenario involving a conveyor belt, where we're going to connect some devices and sensors representing a conveyor belt into the platform. We'll take you through 4 stages: device registration, connection, and firmware updates over the air. We're going to go through data governance with Watson Data Platform, and then we'll move on to dashboards and the developer experience. And we'll finish off with some analytics using data exploration with the data science experience, Jupyter notebooks, and Watson machine learning. Now we're going to do a demonstration of connecting a device to the Watson IoT platform and then updating its firmware over the air. For our conveyor belt demonstration, I've got a Raspberry Pi, which is representing the gateway, and then I've got that connected to a motor controller. In this case, it's an Arduino, which is connected to our motor, simulating the motor on a conveyor belt. I've also got a number of other sensors. I've got a temperature sensor, which we can use to understand more about what's happening in the motor. And I've got an ultrasonic sensor that can tell us more about what's happening on the production line.
Okay, let's go ahead and register the Raspberry Pi that we're going to use as the gateway in our scenario with the IoT platform. To do that, I switch across into the devices view. As you can see, in this instance of the IoT platform, I don't have any devices registered yet. Before I go ahead and register a device, I need to create a device type for it. Every device within the Watson IoT platform has a device type, which enables you to group together similar devices and allows them to share common properties and definitions. So switch across to device types, and I add a new device type. I need to specify whether it's a device or whether it's going to have the special permissions associated with being a gateway. In this case, it's a gateway, and I'm going to specify its name. Here I get to specify additional information like the serial number, model, description and hardware version, and any additional metadata that I want to add to the device type. In this case, I'm just going to take the defaults and move on. Okay, so I've created the new device type of Raspberry Pi. Now I'm going to register a particular device, a particular instance of a device. So I'm going to click the Register Device button, select my existing device type that I just created, and enter its device ID. I get to specify any details that I want to enter about the device, like its serial number, model. In this case, this is a Model 3 Pi, so I'll enter that, and any additional metadata that I want to specify about the device. I now need to enter some security information about the device. I can allow the platform to automatically generate an authentication token for this device, or equally, I can provide the token if I know which token this device wants to use. Alternatively, you could use certificates for authentication. In this case, I'm going to provide a token as I know what I want to use for this particular device. It's important to remember what the token is, because authentication tokens are encrypted and stored by the platform in a non-reversible way for security purposes, but that means that they are also non-recoverable. So here we get a summary of what we're going to create. So we've got the device type of Raspberry Pi, device ID, which are the device uses to authenticate with the platform of Raspberry 01, together with some additional metadata that I've specified, and the security token for the device. Click Done, and I get confirmation that that device has been created with the drill down for the device. If I switch back into the Browse Devices view, I can see Raspberry 01 has been created, its class ID is Gateway, and its device type is Raspberry Pi. I can drill down into the device and look at various bits of information about it. If I look at recent events from the device, we can see that there's nothing currently coming in because the device is not connected. So let's switch across to the device and enter the security credentials needed for the device to connect to the platform.
Before we do that, we need to get the organization ID.
Every instance of the Watson IoT platform has a separate organization ID. We can look this up in Settings, and we can see the organization here. The organization ID, together with security credentials for the device, make up the connection parameters needed in order to connect with the platform. So let's switch across to our configuration file for the device and enter the organization ID. the type of the device, in this case it's a gateway type, the gateway ID, and the authentication token. Okay, so with that saved away, we can now connect the device to the network and have it start sending data into the platform. Okay, let's connect the device. We can see the device is connected thanks to the little dot here. If we look inside, we can see when the device connected, the connection time, and its current IP address, and what form of security it used to communicate with the platform. We also need an entry for the motor controller. In our example, we're using an Arduino as the motor controller, which is connected to the Raspberry Pi and sending events in about the motor and its sensors. Rather than create the entry manually, as we did for the Raspberry Pi, we're going to allow the gateway to automatically register the Arduino for us into the platform. And we can see that that's already taken place. The Arduino has been registered, a device type has been created for it. And if we look inside the Arduino, the definition of the Arduino, then we can see recent events coming in from it. So here we can see the data coming in and being published by the Arduino through the gateway and into the platform. If we click on any one of these events, we can see the content and detail. In here, we can see that there's sensor data coming from the ultrasonic sensor attached to the Arduino, which gives us a measurement of distance. Now on a conveyor belt, that might be a distance to a particular item. If I place my hand in front of the ultrasonic sensor and then click on the event data, we can see that the distance reduces depending on how close my hand is to the sensor. Now we're interested in understanding a bit more about our motor. We want to understand how the bearings are performing in order to make some kind of understanding of how close it is to failure and how much runtime there is left on the device. What we're going to do is add a temperature sensor to the device. So I've got a temperature sensor here, and I'm going to add it on top of the motor so that I can monitor the temperature of the motor and understand how it's behaving. Now I need to do a little more than that. I now need to update the firmware of the motor controller in order to understand these additional sensor readings and send them into the platform. So let's go across and do that in the platform. So first we go across to the Action tab of the Devices view. And in the Action tab, we can see all the actions that have been initiated in the platform against different devices. We have a new instance here, so there are no current actions taking place. Let's initiate a new action to download the firmware, and then once the firmware is downloaded, we'll update the firmware. So select Download Firmware. We need to select the devices that we want to apply this to. In this case, this is our motor controller device type. And here's our particular Arduino device that we've been using as our motor controller. We need to enter some details about the firmware that we want to apply to the device. Let's enter a URL to the firmware that we want the device to use. Let's enter a version. A firmware verifier so that the device can verify that the firmware it's downloaded is the correct version and hasn't been tampered with in any way. And finally a firmware name. These parameters are optional, so I'm going to skip over that one for now. Okay, so we can see that the request has been accepted for processing. The firmware is now being pushed out over the air to the Arduino device representing our motor controller. If we go and take a look at the device, we can see diagnostic messages from the device showing the firmware download taking place, and we can see that it's progressed and it's reached 100%. If we go back and we look at our device action request, we can see that the download has been successful for one device. As you can see, this process is designed to work across many devices and is also drivable from APIs. Now we've succeeded in downloading the firmware, Let's initiate an action to update the firmware. So we click Update Firmware, specify the device that we want to apply that update to. We don't need to specify any of these details again at this point, having specified them the first time, but if we wanted to confirm them to make sure that we were applying the right version, we could do so here. Let's click Initiate. Okay, so that request to update the firmware has gone out for processing. If we do a refresh, we can see that it's been successful. Okay, let's go and take a look at the events coming in from the device. So if we look at the Arduino, we click its recent events, then we can see events coming in. And if we look, we can see that the events, since the firmware has now been updated, we can see events from humidity, temperature, as well as the previous distance measurement that we had before.
Okay, so we've seen device connection, registration, and over-the-air updates. We're now going to move on and take a look at what we can do with the data in terms of manipulation and data governance with Watson Data Platform.
Within the platform, we can manipulate the data coming from devices to make it appropriate and consistent for our applications to use. That might mean normalizing values, such as converting temperature readings in Celsius and Fahrenheit to a common format. Let's take a look at what we can do for our conveyor belt. We define two interfaces, one for the physical device, representing the data flowing from the device sensors. We can see the temperature and humidity, and I've added some more sensors giving us acceleration and gyroscopic readings. We define a second logical interface, which represents the consistent format that applications will use to access the data. We can see that some readings are mapped directly, like humidity. I've added some additional readings which are calculated, like maximum and minimum temperature. The average temperature is calculated from the last 600 event readings. Let's add the compass reading as a direct mapping. Next, I need to decide on notifications on changes to the state of the device. I can choose not to be notified and just use the REST API to periodically interrogate the device. Or I can notify for all events coming from the device, or only notify when there's a change. So if the temperature sensor keeps reporting the same value, it will be ignored and only notify on a difference in temperature. Let's take a look at how that looks with data flowing. If we click on the conveyor sensor and look at the device state, then we can see both the raw data coming in from the device with the temperature and humidity readings that we're familiar with, and then we can switch over to the logical view and see both some of the straightforward values, like humidity, but also our calculated values like minimum and maximum temperature and average temperature. I have a number of options for processing my IoT data. For live data, I can directly connect applications to the MQTT API, or I can connect my IoT instance to Message Hub, a Kafka-based messaging service. To store the data, I can use the Cloudant connector to send the IoT data to a Cloudant database. Let's configure a Cloudant connector to send the data to a database that we can then process with Watson Data Platform. we go to the extensions section, and we can see that we've got a number of extensions that we can choose from. In this case, I'm going to choose the historical data storage. I can connect it to any one of my cloud instances. I'm going to select this one. I get some options to configure the bucket interval, the time zone for timestamps, and a name for the database. I'll just stick with the defaults for now. And I complete the connection by clicking confirm. That was successful. And we can now see that the historical data storage is configured. This is the Watson data platform. In this scenario, I'm a data steward who's going to use the platform to shop for information and then move it into a project so that I can do some data science upon it. The idea is that we've built a catalogue that provides all the information assets across the business, regardless of which systems they're stored in, whether they're stored on-premise, in cloud, or anywhere else. And we provide a catalogue where it's very easy for the knowledge workers to find the information and get productive use from it. The first thing I'm going to do is go into my catalogue. The catalogue is really the single place where our users can go to find any of the information assets that are available for their use. Now in this scenario, I know I want to find IoT data. So I'm going to filter my catalogue, and I can see that there are some interesting data sets that may be useful to me. Conveyor dataset looks like it would be an interesting dataset for me to use. So I'm going to click on that dataset and look at the metadata for that asset. So I can see information as to where it came from, and I can see any of the column information that's available inside the dataset, along with a sample of that data. I can also see profile information, so as we're cataloging data, we're also running a number of profilers on that data to determine if we can understand which business entities exist inside that dataset. So here, we've got IP addresses, for example. I can also click on the Profile tab and go a little bit deeper and look at the confidence in the profiling information. If we look at the IP address, for example, we can see that we're 100% confident that this is actually an IP address inside the column. Okay, so I'm happy with this, that this data set is going to be useful to me for my data science project. So I'm going to go ahead and add it to my project. By adding this asset to my project, that means I've copied a reference to that asset into my sandbox so that I can gather all the assets I think may be useful to me inside that sandbox and then use that sandbox as a way to do data science. Let's go and find some other assets. I can see I've got an IoT asset that's been recently added to the catalogue. This could be of interest to me. Oh, I can see that my access has been blocked. The reason that we've been denied access is thanks to the modern approach to data governance that's provided by the platform. As we're opening up information to self-service analytics, the active, actionable governance engine baked into the platform determines which users should or should not have access to this information based upon rules. This is really important to be able to power self-service analytics, because without this, you're opening up data with no control. So if we're going to allow this data to be open for analytics, we really need to make sure that we've got a modern approach to data governance to be able to apply policy information. The system gives you a rules builder to create policies and rules, and those govern the impact that happens onto the users of the system. So we've gone through and we've shopped for information and found the assets we want. Now we're going to go into the project that we created, our conveyor analysis project, and we're going to be able to see the assets that we added to the project. So here we can see we added our conveyor data that we pulled from our catalogue, and now it's available inside our project. The idea being that we gather all this information together and then we're able to use it to run data science upon it. Inside our project, we preview our data, and here's our dataset. We want to be really confident that this is the right dataset we want to use. So before we go and get access to the data and create a data pipeline to move the data, we're going to launch our refinery tool, which will allow us to do some slightly deeper analysis on that data and ensure it's the data we want to use. Also, it will allow us to build a pipeline to extract the data from that remote source and move it into a format that you want so that we can use it for our data science. This is our data shaping tool, and we have a whole ton of operations that we can use for data shaping. For example, we can convert the type, filter column information, we can replace values, empty values, split columns, and a whole bunch more, all based upon the data that's there. We can also use R scripts if we want to, and we can build up various R scripts to shape that information. If I go into the Profile tab, then we have a slightly more in-depth view of the profile. We can see the different values that exist across our different datasets, which could be interesting. We can also very quickly on the fly build out graphs to understand the different values that exist inside our dataset. So we can see, for example, that in this dataset we have a good split of temperature values. So we can use that to understand whether or not this is a good dataset for us to use. In this case, we're confident that this is a good dataset, and we're going to go ahead and run our pipeline. To run our pipeline, we can choose whether we want our dataset to be written out to another database somewhere, or we could write it to a CSV file. In this case, we're going to run it into a CSV file and create an extract from our remote source, which happens to be an object store, and pull it into a local file so that we can then use that with data science or self-service analytics. So that job is now going to run. And in the background, behind the scenes, this job is running on Spark. It's going to connect to the data source, build that extract, stick the extract once it's completed back into our project, and from that point we can do the data science upon it. While that extract is running, let's take a look at the governance dashboard. So I mentioned earlier how we were shopping for information, and we had a policy enforcement engine that was preventing access to that information. The governance dashboard provides a view to show over time how different access to different datasets through the Shopping for Data portal has been denied by different policies over time. And this is very important because in our view, you can't have a self-service analytics platform unless you have some kind of actionable governance that will police the way in which access to the data is controlled. So if we go back to our project, we will now see that we have a new asset that's been created. There's our shaped CSV file. The extract has been pulled from our data source so that we can use it to create notebooks and run data science on it.
Okay, we've seen what we can do with the data platform. We're now going to push on and have a look at the developer experience, some of the dashboarding that's available within the Watson IoT platform.
So let's take a look at systems management and the facilities that the IBM cloud environment offers us. If we look into the catalog, we can see that there are many services that we can pick from. If we pick the Internet of Things category, for example, we can see the Internet of Things platform there, which we can deploy. If I switch into my dashboard view, I can see all the applications and all the services that I've got deployed, including my Internet of Things services. If I click into an application, I can see how much memory it's taking, its total memory allocation, and the general health of each application. I can check that it's running, and I can link off to the actual deployed instance of the application and see the application that's running. I can see connections to other services, and I can look at the logs and see what's been going on with my service. I can also attach facilities for monitoring and apply API management if I choose to. Back in the IoT platform, I've got a selection of dashboards that I can use to view both data about the system and data about my devices and how they're behaving. One of the built-in dashboards is the usage overview. Within it, I can see different types of devices and how they're allocated between device types. I can see how much data I've transferred both today, this month, the previous month, and a graph of how that's tracking forward, so I can understand my costs. Before we define our own board, I'd like to show you the device simulator, which is a really useful tool in terms of our developer experience, and makes it very easy to simulate one or many devices when you don't have the physical devices in front of you or want to try out a new set of data. So if we open the device simulator, we can add a first simulation. We pick a device type for the data that's going to come in. We can see that the tool has automatically picked up from the physical interface the definition of the schema of the data that's going to come in from the device. We can override some of these values, perhaps provide a range. And save that away. Now in this case, I've pre-prepared a schema for this simulation, so I'm going to import the data from the clipboard. Let's create a dashboard that will allow us to easily view the data that we're now sending in with our simulation. Here I can create a new dashboard. I can give it a name. I can choose to make it my landing page or make it a favorite. I can choose who to share it with. I can share it as read-only with everyone or add individual users. Okay, so I've defined a new board. Inside the board, there are a collection of cards. I currently have no cards. Let's add a card. I'm just going to create a simple board for this one, so I'm going to display the temperature coming off the devices on a simple gauge. I pick the device and I pick a data set. In this case, we're going to pick temperature. I tell it what the type of the data is. It's a float, and I can give it a unit. And I can adjust the minimum and maximum values. And then I can pick the style of the card that I'm creating. I can adjust the color scheme. And give it a new name. And there we go. I can obviously build up much more complicated boards. So here's a board I prepared earlier. We've got a selection of different widgets on here. We've got the gauge widget that we saw earlier. I've got a line chart widget, which is containing the acceleration readings that we're getting from our sensor in the X and Y directions. I've got a chart with the compass readings on, and down here I've got a bit more detail on my devices. These charts are connected and responsive, so if I click on conveyor sensor 01, it then gives me the drill down detail on the device info, the metadata about the device, and this one updates with the live properties going on, so we can see the real-time values in X and Y and Z acceleration, as well as other properties coming in from the device. These dashboards are very useful for system administrators, and they make it very quick to be able to build up a quick panel of understanding what's going on in your system and then being able to save those away and refer to them later. But often you'll want to build a portal for your users using the real-time feeds and data and information which is available from APIs. I've got such an example here. This is an application running on IBM Cloud which makes use of the APIs to read the data from the device. So we can see that we're plotting the current temperature, which varies. We're plotting the average temperature, which we created earlier, along with the maximum and the minimum temperature. And we can see those values coming in real time on the graph. Another example is the conveyor belt simulator in our Getting Started guide. The code for this is available publicly on GitHub. And if you scroll down, there's a button which will automatically deploy the code for this and run the toolchain in IBM Cloud to be able to deploy this application and get it running. If you click that and follow through the tool chain, then you'll be able to see the conveyor belt demo and see data flowing into the platform. Let's show an example of building a rule that will send an alert when there's a problem with the conveyor. In this case, we'll use a simple example that alerts the operator when the motor exceeds a certain speed. If I go into the rules section of the platform, you can see I've created a rule already. We can see this rule is set to apply to things of type IoT conveyor belt. The rule is divided into two sections: triggers that define when the rule will be called, and actions that say what will happen when the rule is executed. We can add one or many conditions. In this example, we're looking at the RPM property, and we have a number of operators that can apply to it, either comparing with static values or another property. It's useful to be able to control how often alerts are sent when conditions are met to prevent being overwhelmed with notifications. For example, we can set to only trigger if the conditions are met once in a minute interval. If I edit the action, you can see that there are different types of action that can be performed, including email, if this then that, Node-RED, or webhook to call any web service. If I switch back to the conveyor simulator and speed up the conveyor, we can trigger the alert. If I look at the device-centered analytics board, and click on the device, we can see the alert that was fired. Another important aspect of systems management is security. We can configure security on the Security tab here. We can define security policies that govern how connection security is configured. If we go in and edit the connection security policy, we can see that we can define how devices are allowed to authenticate with the platform using TLS, tokens, device certificates, or some combination of those. We can define additional custom rules for specific device types to override and allow a different type of security for a given device type. We can also configure black and white lists. So if we have a look in here, then we can see that we've configured a rule that excludes a particular country from being able to connect to the platform. We can do it using IP address ranges, we can use a CIDR, and we can specify particular countries for inclusion or exclusion to the black or white list in terms of connecting to the platform. We can view all of this together on the dashboard. If we go to the risk and security overview, we can get a view across our system of how many devices are compliant, how many are passing in terms of their connection security policy, whether devices are being blocked due to the black or white list, and how the general compliance of the system is behaving.
Okay, so we've understood some of the developer experience, we've had a look at the dashboards and the platform. We're now going to look at analytics and move into data exploration with data science experience, Jupyter Notebooks, and machine learning.
In this section, we're going to move on to analysing the data. We're going to analyse the data from a motor bearing to determine early signs of failure and to prevent outages. We're going to store some sample data from the Watson IoT platform into object storage. We'll annotate that data with information about whether the data represents a good or a bad reading from the bearings. We'll then use that data to build a supervised machine learning model using data science experience. We'll then deploy that machine learning model with Watson Machine Learning. Deploying the model will create a REST endpoint which we can send live data to in order to check the health of a real bearing. Additionally, we'll show you how you can produce multiple models simultaneously using Jupyter Notebooks and set a schedule to periodically update the models with the latest information. We'll finish by showing an alternate approach using Keras and TensorFlow to build an unsupervised model using neural networks. This part of the demonstration adds some additional services to those we've seen already. As before, we have an instance of the Watson IoT platform, including its MQTT message broker. For data storage, for analytics, we'll add an IBM Cloud Object Storage, which is very cost-effective for large amounts of data. IBM Cloud Object Storage includes flexible storage classes for frequently accessed data, occasionally accessed data, and long-term data retention. We could also use other databases like Cloudant or DB2 Warehouse, as we used in the earlier sections. Finally, for the analytics heavy lifting, we will use an instance of the IBM Analytics Engine, which is in turn backed by Apache Spark and Kubernetes to provide elastic analytics processing power. Throughout this demo, we will use accelerometer sensor data sampled from a physical model, the Lorenz attractor model, in order to simulate bearing vibrations. We can change the model to produce healthy or broken bearing data. Using the flow component in IBM Data Science Experience, we directly stream this real-time data from the IoT platform to object storage. Once data has arrived in persistent storage, we are ready to perform some batch analytics. There are various ways of achieving this. We can use the graphical user interface for simple operations, or we can code on top of open source or proprietary machine learning and deep learning libraries. We're now going to create a machine learning model using our sample data to train the model. Using the graphical interface, we can simply drag and drop a time series of healthy and broken bearing data to the panel. This data is already labeled as healthy or broken and is therefore suitable for supervised machine learning. The first column contains a binary label where 0 means healthy and 1 means broken. We then define the schema of our data. You can see that the system has inferred a draft schema for us. We can edit the schema at this stage if needed. The main thing we need to do is to specify which column contains the label to say whether the data is healthy. We define column 1 as a binary value and set it to the target. This tool is suitable for beginners and includes some useful nodes to simplify the task. For this type of problem, we can use the Auto Classifier node. This node automatically creates a composite classifier out of various state-of-the-art algorithms, including support vector machines, random forests, gradient-boosted trees, and neural networks. The Auto Classifier has automatically picked a suitable algorithm or set of algorithms which best fit our data. Once the model is trained, we can inspect it using the table node. The table node will show us how the model has classified the data and its confidence in the result. If we see high confidence in both healthy and broken results, then we have a model that we can continue working with. Let's have a look at the data. In this row, we have a healthy sample, and the model successfully predicted healthy. The last column gives us a report on how confident the model was in its evaluation. In this case, we are seeing almost 100% confidence. The same holds for a broken sample, where the model predicted that it was broken, with nearly 100% confidence as well. So far, we've been exploring the data and developing a model. If we want to use that model in a live system, then we need to deploy it. Let's deploy this model to IBM Watson Machine Learning to make it accessible to applications by creating a REST scoring endpoint that can then be called from any application. We just select a name and a Watson Machine Learning instance running in the IBM Cloud as its target. If we now refresh the dashboard of Watson Machine Learning, we can find the newly created model. Now we deploy the model. Here we can see all the information required to use the model from an application. To make it easier, corresponding Swagger REST API documentation is generated automatically. Data scientists often prefer the full power available from the underlying tools and runtime. Here, we can use Jupyter notebooks with Python and R to rapidly develop machine learning models. As before, we're going to create a machine learning model, this time using Apache Spark ML. The notebook makes it easy for us to create models for multiple sensors. In this case, we'll use a gradient boosted tree and deploy it to Watson Machine Learning. This example has trained and deployed 30 models in one go. Again, we can create REST endpoints for making these models available to applications, either using the user interface of Watson Machine Learning, or alternatively, using an API-based approach. If we are happy with our code, we can schedule the notebook to be executed on an hourly or daily basis. This approach allows us to automatically update our models with the latest data. The field of deep learning and artificial intelligence is a very hot topic, and the open source community is making strong contributions which are continuously being updated and improved. Combined with traditional machine learning solutions, IBM embraces this open source community and aims to support all open source frameworks within the platform. As an example of this, we'll now show how Keras and TensorFlow can be used within the platform for anomaly detection. Data scientists often like to perform rapid exploratory analysis of the data. This can be done directly in the platform using notebooks. Here we examine our vibration sensor in both the healthy and broken cases. We can also have a look at the frequency spectrum of the signals by transforming from the time to the frequency domain using a discrete Fourier transformation. These tools make it easy to play around with neural network topologies to create good results. Now we can run some tests. Since this is an unsupervised machine learning anomaly detector, we test 10 times with healthy data, and finally, we show broken data to the model. We can clearly see the gap on the broken data set. This model seems to be performing well. Let's create a real-time system out of this. If you remember back to the beginning, our input data from the motor bearing is the vibration data in 3 dimensions arriving as a stream. Now let's connect to that stream directly from the notebook. We fill a buffer with a count-based tumbling window, including 30 seconds of data, and we then send this window downstream to the neural network for analysis. The resulting anomaly score we then send back to the IoT platform using MQTT so that the other IoT devices can pick up the score and take an action. The action could include alerting an operator or shutting down or slowing the motor before damage occurs. Here in the IoT platform dashboards, we can see both the input data and the anomaly score based on the bearing vibration data.
So in summary, we've walked you through various capabilities of the IoT platform We've been through device connection, data governance, taken a look at dashboards and the developer experience, and then finished off looking at some analytics. I hope you've enjoyed the show.